So hello everybody, back again to your last class on this last module of your computational physics paper. And in this class we are going to discuss planetary motion, that is Kepler's problem. And you are well familiar with three Kepler's laws of planetary motion. And the first law states that every planet revolves around the sun in an elliptical orbit with sun as one of its foci. And what is second law? Yes, it deals with the aerial velocity, constant aerial velocity. The radius vector drawn from planet to the sun sweeps equal area in equal interval of time. Or you can say that radial velocity is a constant. That is dA by dt is a constant. And third law states that the square of period of revolution, t square, is proportional to cube of semi-major axis of the ellipse. Here we are going to discuss the elliptical orbit law. So this is something you have studied in your degree classes. That is, every sort of planetary motion is governed by gravitational force, and gravitational force is a attractive inverse square law force. Attraction means the force will be having a negative sign. Inverse square means force is proportional to r square, that is proportional to 1 by r square. So normally if G is the gravitational constant, m is mass of the sun. Suppose we are taking the planet Earth, which is of mass small m, revolving around sun of capital M. And so from we'll get acceleration F is equal to minus gmm by r square, attractive force. Acceleration is minus gm by r square. And normally we know that all sorts of planetary motions are confined to a plane. That is, even though there occurs a small tilting in the plane, it is assumed to be, suppose our Earth is revolving around the sun in xy plane. Suppose at any instant we assume the motion of the Earth such that we assume the coordinate system which we use to describe the motion of the Earth around the sun to be the center of the sun, such that our Earth of mass m is at a distance r from the center of the origin of our coordinate system, making an angle theta with the x-axis. In a routine process, you have x is equal to r cos theta, y equal to r sin theta, x square plus y square is equal to r square, and cos theta is equal to x by r, sin theta is equal to y by r, and ax is equal to, it is actually a crude method. It gives you the equation of the circle even though we are trying to simulate an ellipse. Okay, so bear with it. Ax is equal to minus gm by r square, that is x by r. And so what you will get? Ax, similarly, a component, if acceleration having component along x direction and y direction, I can resolve the acceleration along x to be a cos theta, and a is minus gm by r square, and cos theta here is x by r. So I will get ax is equal to minus gmx by r cube, and you know r square is x square plus y square, so r cube is x square plus y square all raised to 3 by 2. Right. So you have ax is equal to minus gmx by x square plus y square all raised to 3 by 2. Similarly, from that acceleration along x direction, I can find out the velocity and position coordinates along x direction using the Euler method that you generally use. Similarly, along y direction, it is y direction here, it's not x. Ay is equal to minus g by r square into y by r, and y by r you got it from minus g by a sin theta. Sin theta is y by r, and in a similar substitution you will get ay is equal to minus gmy by x square plus y square all raised to 3 by 2, and from that you will get y component of velocity and y coordinate at any instant of time. So we are going to try to have a program, and you know gravitational force is a conservative force, and here we can write velocity to be dr by dt, and our acceleration a is equal to f by m is dv by dt, and f is equal to minus gmm by r square. These are all the things that you know prior. And planetary motion from PyLab import star. Actually this g values, m values are very bigger values. For the sake of simplicity of the problem, we assume gm to be some 10 unit, and 1 unit will be having some value, and we assume it to be 10 unit for the sake of simplicity, and I assume x to be x coordinate, initial value of our initial x coordinate of my earth to be 20 and y coordinate to be 0, and r is equal to x square plus y square root. And we know the expression for velocity. It is square root of gm by r. We normally get a circular path. And for different values of velocities, for lower velocities or higher velocities, we'll get elliptical or hyperbolic path, and you can choose f is equal to 0.5 means you get elliptical path. If I'm putting f is equal to 1 means I'll get circular path, and you can try varying f such that velocity varies and we get different trajectories showing the planetary motion. And what we want to get is, according to Kepler's planetary motion problem, elliptical orbit. So I've chosen f to be 0.5. And similarly, x component of velocity is assumed to be 0. Y component of velocity is square root of gm by r into f. H is time step, that is 0.05. And in order to plot what we need a list of values. So I initialize a list for x pose, a list for x, similarly y pose, a list for y, and we work out with a for loop which works actually 30,000 times, and you give the value of r, you give the value of x. Vx is what? Gm by gmx, gm into x by r cube is what? You have given r to be x square plus y square all raised to 1 by 2 is what? It is actually x component of acceleration. The minus sign is from that equation, that is attractive force. We'll put a minus sign here, and h is the time step, and this is actually the Euler method. And similarly, we'll have vy component in the similar way. And from these equations, you can find x and y values in a similar manner. And what you do next is, in order to plot or get the graphs, you need to append these values for x and y to the corresponding x pose y pose list. And this loop will work 30,000 times, and when it reaches 30,001, it comes out of the loop and it plots x pose y pose. Okay, and x label y label axis is given equal and show. So you get the graph like this way. So this is what the planetary motion says. X versus y graph, you get elliptical orbit for, and you can change the value of f so as to get different shapes. And while dealing with these problems, or while dealing with computational physics problems, there may be a lot of errors since we use numerical method. Numerical method means we deal with numbers through iterative process. So normally there will be chance for errors. Basically, a lot of errors occurs basically with numerical method problems, and two types of errors that we come across is truncation errors. It refers to the error in a computation which involves the sum or sum of product of terms of some finite or infinite series is truncated. For example, in the computation for the value of cos x. Cos x is what? Nth term for cos x is minus 1 raised to n x raised to 2n divided by 2n factorial. And the series is truncated for a given value of n. Suppose n is 5, so that error will be order of x raised to 12 by 12. So what happens is that when step size decreases, truncation error also decreases. When step size increases, truncation error increases. When we have small step size, the truncation error decreases. And what happens with round-off error? Round-off error occurs because of the computer's inability to deal with large quantities. And the value of phi is 3.14, a big tail will be there, and we normally round it to 3 or 4 decimal parts. Similarly, 1 by 3 is represented as 0.3333, etc. And the interpreter or the microprocessor, depending upon the system, will truncate it to a certain value. So what happens? There also the errors occurs, and this type of errors is known as round-off errors. So what happens here is that when we are having smaller step size, means we are doing repeatedly a large number of calculations. So once it is truncated, there will be an error, and the number of iterations or number of calculations increases. The quantity or the volume of the error also increases. So when step size decreases, round of error increases as the number of iterations increases. The other case was as step size decreases, what happens? Truncation error increase. Graph for truncation error, and this is the graph for the round off error. And round off error, you know that when step size is smaller, you'll have to do a large number of iterations, which makes the probability or possibility of increasing the error as the number of iteration increases. So for smaller step size, large number of iterations and larger error, and the step size increases, smaller number of iterations shows smaller error. This is the diagram for the round off error, and this is what describes the truncation error. And the truncation error arises due to these kinds of effects we have already discussed while doing the calculations for certain mathematical values and all. We'll have to stop it somewhere, which causes the error. Truncated, the series is usually truncated below for cos series n is equal to 5, so that the error creeps in. And this also happens in the case of Euler method. What we are doing, we find the velocity to be constant for a given value of step size. Actually, velocity is what? We write new velocity is equal to old velocity plus acceleration into time step. So what happens here is that for a given value of time step, velocity is assumed to be constant. But actually it is not true. Velocity is a continuously varying quantity. If we are taking larger time step, velocity in that time step will be varying quantity. So if you are taking smaller time step, means what happens? Our result will have less error, and if we are increasing the time step, the chance for the errors also increases. This is what is happening in truncation error. Especially truncation error is higher when using Euler method, since velocity is a varying quantity and position is also varying continuously. I assume that for a given time step h, velocity is constant. So this will be true only if the time step we are taking is very small. So for the smaller time step or the smaller step size, truncation error will be smaller, and for a larger step size, truncation error also will be larger. So this is all about the truncation error and round off error. And there is no rule for selecting the step size, and we do actually a trial and error method, and we optimize the step size by giving consecutive values. And here I can say that this will be the net error, which will have a lower value at the point of intersection of two errors, and I can optimize the step size to be here in this case. Okay, in this way you can optimize the step size. So hope everything is clear for you. Go through this, and while dealing with this planetary motion, you try to do the coding in RK method and do it as an assignment and send to me. Only change is that change this loop construct and write the coding according to the RK method, putting K1, K2, K3 and K4, and do the coding as an assignment for the RK method and send to me. What is written as an Euler method, you do the coding in RK method as an assignment and send to me. Okay, thank you. So see you in the next class. Thank you.